For information program and others in the Annenberg CPB collection, call 1-800-LEARNER.
Funding for this program was provided by the Annenberg CPB project.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
a bay at sunrise. Beneath the beauty, a natural process is affecting marine life. How much change can the fish take? A river, bubbling with pollution and controversy. How much of what is harmful to health? A drinking fountain. Healthy teeth depend on the fluoride added, but what is the right amount? The answers depend on chemical measurement. It is not enough merely to ask what is there. It is essential to determine how much, and to be sure the measurements are accurate. Measurement is truly the foundation of chemistry.
Welcome to the laboratory. Look at all the stuff around. Glassware, instruments, bottles of chemicals. An experiment is going to begin. But before we begin, we have to measure. In order to help us measure, to help our senses, what we have done is to invent a number of devices and instruments. Here is one of them that you're familiar with. That's a thermometer. Some others are over here. This is a burette, an ingenious device for delivering a very precise volume of a liquid. Here is a modern analytical balance. But you know, there's really nothing new about our concern with measurements. I recently went to a museum and saw some 5,000-year-old clay tablets. And do you know what was recorded on them? A dispute on weights and measures. Why is it that measurement has been so important to us throughout history? And in particular, why is it that accurate and precise measurement is at the heart of modern chemistry?
Measurements are made nearly everywhere. Take your local gas station, for example. There's volume and pressure. Electric current, wheel alignment angles, ignition voltage, engine speed, specific gravity, spark plug gaps, and exhaust emissions. They're all determined by measurement. Try to imagine a part of your day that doesn't depend on measurement. Most of our activities could not occur without measurements. It forms the foundation of modern science and technology. In medicine, scenes like this are repeated countless times each day as researchers measure the chemicals in our bodies. Treatment and appropriate medication depend on measurement. At the submicroscopic level, measurement of DNA structure has helped to unlock our genetic code. And beneath our Earth, measurements guide scientists as they draw samples and analyze them in the laboratory. In manufacturing, chemical measurements control the makeup and strength of products. Measurement makes the steel for our cities stronger, then fits our cities together. The purity and composition of what we eat, what we drink, and what we breathe all depends upon chemical measurement. Every day, we rely upon these measurements to guide us through our lives without giving them much thought. To the scientist, however, measurement is a constant search for the true value of what is being measured. How do chemists accomplish this goal? Series demonstrator, Don Showalter.
Chemists are always measuring things. Their goal is to get as close to the true value of the measured quantity as they possibly can. What is the true value of the mass of this antacid tablet? Let's weigh it on this balance. It weighs 1.1 grams on this balance. I have a second balance. It's a little bit more sensitive. By more sensitive, I mean now that this balance weighed to the first decimal place, to the 10th of a gram. Whereas this one now weighs to the third decimal place, to thousandths of a gram or a milligram. It weighs 1.137 grams. But is this the true value of the mass of this tablet? Now this is an analytical balance. It's one that chemists commonly use to measure small masses. Let's see what it weighs on here. Now, this should be the most sensitive measurement, the one closest to the true value. It weighs 1.1362 grams. But I have a question for you. How do we know that this balance is giving us an accurate measure of the mass of this tablet? Actually, we can't be sure unless we've already done an important step. Now, this object is called a standard mass. It might be tiny, but it has a very important function. It weighs exactly 1 gram. Now, if this balance shows us that, then we'll know it's working properly. As you can see, it is. But I have two far more basic questions for you. How do we know that the mass of the standard is exactly 1 gram? And how do we know that what we are calling 1 gram is the same measurement that everyone else is calling 1 gram?
Part of the answer rests in this safe, protected by contact alarms and a special glass container. It sits in the sub-basement of a government agency near Washington, D.C. This is the standard kilogram, the mass standard for all of the United States. All measurements of mass that are done in this country start with the standard kilogram as a reference point. The National Bureau of Standards keeps the kilogram here at its national headquarters. The chief concern of scientists at the Bureau is measurement. They are devoted to designing and testing new measurement systems, then refining them to increase their accuracy. They also maintain the standards for every other type of measurement that we do. Why are standards so important? Stanley Raspberry is director of the Standard Reference Materials Division.
A standard in this case is an actual physical embodiment of weight or mass. And it can be intercompared in different countries and in different places within the same country so that people always agree that this is a given mass. Most of analytical chemistry ties right into the kilogram because in analytical chemistry, the job of the analytical chemist is to decide how much there is of specific elements or specific molecules in a mass of a product.
But long before chemists began using standards, they were being used to ease international trade and communication. Early standards weren't always practical. For example, the basic standard for measuring length used to be the king's foot.
But of course, the king in Germany would have a different length of foot than the king in France or the king in England or the king in Italy, so this could lead to very serious trade problems, communication problems. It doesn't really matter too much what you define a meter to be. You could define it as a very small length, like the length of your pen. But unless everyone in the world agrees that that's a meter, then you don't have a standard of measurement that's adequate to today's world.
Scientists also use standards to ensure that their measuring devices are working properly. For testing balances, a weight that has been certified by the Bureau of Standards can be used. However, with more sophisticated measuring tools, a different type of standard is needed.
90% or more of the practical work done in analytical chemistry is done with instruments. And the instrumental analysis requires some kind of measurement standard to be run right on the measuring equipment. You don't go to a balance at all. You don't separate out elements at all to be weighed on a balance.
This mixed diet is an example of a standard that can be run directly on a measuring instrument. To prepare it, scientists start by gathering what statistical studies say is a normal diet in different regions of the country. The food is cooked, then mixed together. The resulting mush is freeze-dried. Next, the key elements are measured in several independent laboratories. When all the independent measurements agree, the amounts are certified. The freeze-dried diet can now be used as a standard.
Taken with its certificate out to the nutrition lab, it becomes a very important quality assurance sample for nutrition chemists. They're trying to find out how much selenium is harmful, how much aluminum is harmful, or are those essential elements? Perhaps you need 1 part per billion of selenium, but if you get 100 parts per billion of selenium, it becomes harmful. And as they make all those studies, they need accurate analyses. This kind of material helps them to home in on that accurate analysis by being able to run this material and check and see if they get the certified value for the selenium or the arsenic or the chromium or the nickel, copper, any of the other elements that are in this average human diet.
We've just seen how important standards are in measurement, because unless we agree, we can't be sure that the measurement is right. Here is a body of water. I think it might be polluted. You know, if I wait for the fish to come up to the surface dead, that's much too late. The environment might be gone at that moment. What I've got to do is to detect a possible pollutant at a part per billion level even. How do chemists come up with ways of measuring such small amounts?
A bay at sunrise. It has a unique beauty, yet Chesapeake Bay typifies human interaction with the oceans, streams, and lakes of our planet. Because the bay is so valuable to us, researchers are constantly at work studying its chemistry. They also monitor the effects of this chemistry on the plants and animals living in the bay. Chesapeake Bay is an estuary, a huge mixing bowl for fresh and salt water. Each day, large amounts of fresh water from streams flows into salt water from the Atlantic Ocean. So parts of the bay are more saline, more salty than others. Marine life is affected, and so are the livelihoods of fishermen. For saltwater fish can die if salinity is too low. So government agencies constantly test the bay's salinity levels to within a few tenths of a %, or within several parts per thousand. They do this by taking samples of water from the bay at different sites and on different days, in order to gain a picture of the bay as a whole. But once the samples are taken, how is the level of the salinity determined in the laboratory?
Frequently in nature, as well as in the laboratory, we are dealing with substances that are in solution. It very well might be difficult to separate out the components and weigh them. What we can do is directly measure the concentration of the sample. That is, the amount of substance dissolved in a certain volume. The technique we will use is called titration. The first step is to prepare a standard solution, in this case, a solution of silver nitrate. We would weigh accurately on this balance a certain amount of silver nitrate, in this case 1.00 gram. We would introduce that silver nitrate into a flask like this. We will then add water to dissolve the silver nitrate and finally dilute up to a volume of 100 milliliters. We now have 1 gram of silver nitrate dissolved in 100 milliliters of solution. That is 0.0100 gram of silver nitrate per milliliter of solution. We would introduce this solution into this device called a burette.
The burette, a long slender tube with volume marks on the side, will allow us to add the solution of silver nitrate drop by drop to this sample of Chesapeake Bay water. The bay water must be stirred during the process to ensure a complete mixing of the silver nitrate and the chloride.
When we add the standard solution of silver nitrate to this sample, a chemical reaction will occur. I'm adding this substance so that we will be able to tell chemically when the reaction is complete. We need to add the standard solution very carefully in order to perform an accurate measurement. As we add the standard solution to the sample of Chesapeake Bay water, it turns milky white at first. The silver nitrate in our standard solution is reacting with the chloride in our bay water. The chloride is the substance that determines how saline the bay water is. So we want to find out exactly how much of it is dissolved in this sample. Now see the pink color? This means that all the chloride in the sample has reacted with the silver nitrate in the standard solution. We have used 22.5 milliliters of standard solution. Each milliliter contains 0.01 gram of silver nitrate. This means that 0.225 gram of silver nitrate has reacted. Now, using this information, we can then calculate the exact concentration of chloride in the sample.
But salinity measurements are only a small and relatively easy part of the effort to discover what affects the nation's waters. Other substances are present in only very minute quantities, in some cases, just a few parts per million. Take mercury, for instance. In the 1960s, mercury residues were found in fish coming from the English Wabigoon River in Canada. Several members of the local population were severely affected. Mercury poisoning can cause serious neurological damage, resulting in weakened muscles, loss of vision, and loss of brain function. And it can cause death. Researchers discovered that certain bacteria in sediments at the bottom of rivers and lakes convert metallic mercury into a slightly soluble and thus highly dangerous compound called methylmercury. The source of the mercury in the Canadian waters could have been the nearby pulp and paper mill. Some industrial plants have been dumping as much as 100 kilograms of mercury every day. In response, officials in Canada and the United States began to prohibit discharge of mercury from industrial plants. The Food and Drug Administration now allows only 1/2 of 1 part per million of mercury. This means that only 1/2 of a milligram of mercury can be present per kilogram of water. How do chemists measure such small amounts?
To find the concentration of a small amount of a dissolved substance such as mercury, we use a method called spectrophotometry. Now, this is a spectrophotometer. It measures the amount of light that a substance absorbs. The measure that it gives us is called absorbance. Let's see how it works. Remember when we were weighing the tablet, how we used that standard gram to make sure that the balance was accurate? We should do the same thing when we make our mercury measurement using the spectrophotometer. Now, this is a blank solution. It has no mercury in it. When we put it into the spectrophotometer, it should measure 0 absorbance, as it does. The next step involves something that we've talked about in an earlier part of the program, a standard solution. Now, this is a standard solution of mercury. We put it into the spectrophotometer, and this is the absorbance.
To find the unknown concentration of mercury in the sample, we will eventually need to compare its absorbance with the absorbances of different concentrations of the standard solution. The first step in that process is to construct a graph matching the known concentrations of the standard solution with their absorbance measurements from the spectrophotometer. The known concentration of the undiluted standard solution is plotted on the x-axis, and its absorbance in the spectrophotometer is plotted on the y. A point is placed where the two lines intersect.
Now, this point isn't much use to us by itself. However, if we would accurately dilute our standard with a measured amount of water, something interesting begins to happen.
Additional measurements are made on lower and lower concentrations of the standard solution. The points form a line called a calibration curve.
Now we are ready to find the unknown concentration of the mercury in the sample. But first we need to get its reading from the spectrophotometer.
The sample's absorbance is plotted on the graph. A line dropped from the calibration curve to the x-axis gives us the unknown concentration of mercury in the sample. In most experiments, scientists perform measurements at least 3 times and compute the average. They do this because repeated measurements of the same sample are never exactly the same. There's always a certain amount of error in the measurement procedure and in the measuring instrument. When the same average is found using different procedures and instruments, it becomes accepted as the true value of whatever's being measured. Scientists try to make their measurements carefully to ensure that they're accurate. A set of measurements is accurate if the average is close to the true value. In addition to accuracy, scientists also strive for precision in their measurements. Precise measurements are those that are clustered tightly together. The tighter the cluster, the greater the precision. It's possible for measurements to be precise and not accurate. A tight, precise cluster may have an average that's far from the true value. It's also possible for measurements to be accurate and not precise. Widely scattered, imprecise measurements may still average out to the true value. But imprecise measurements are a sign of uncontrolled fluctuations in measuring instruments and procedures, so scientists try to avoid them. A scientist's goal is to obtain measurements that are both precise and accurate.
Debbie, really? Dentist says no new cavities.
Fluoride's first promotion. Today, in our toothpaste and water, we take fluoride for granted. But it took extremely accurate and precise measurements to discover how much fluoride was beneficial. Tom Reeves is the National Fluoride Engineer for the Public Health Service.
Fluoridation has a very interesting and intriguing history, and it started way back in the very early 1930s, when a dentist went out to Colorado Springs, Colorado, to start his practice. And when he had a lot of the children come into his office, he noticed that they had a brown stain, and he called that a Colorado brown stain.
The dentist, Dr. Charles McKay, discovered something fascinating about the children with Colorado brown stain. Although their teeth were discolored, they had almost no cavities. McKay suspected that something in the local water supply was responsible. It was fluoride, but in very minute amounts.
When they had finally determined that fluoride chemicals was the material that was causing the brown staining, they couldn't determine at what levels the problem existed. For example, was it 1 part per million? Was it 100 parts per million? Was it a half a part per million? And part of this problem was they could not measure it at that lower levels.
It took years to develop a technique that could accurately measure small concentrations of fluoride. Then more research was needed to discover the proper amount to prevent cavities. Finally, they identified it. 1 part of fluoride for every 1,000,000 parts of drinking water.
Here you were that we had something in our very fingertips that we could inexpensively add or subtract to the drinking water and virtually wipe out or greatly reduce dental caries. I mean, it was really an astounding thing.
Today, the fluoride in your water is closely monitored. If the concentration is too high, the Colorado brown stain or fluorosis could result. If the concentration is too low, you can get cavities.
I can't think of anything that more clearly shows the importance of measurement than the fluoride measurement. It's the key to solving the mystery in the 1930s. And it's also the key to getting an accurate amount of fluoride in the water today so that you get the full dental benefits, but you don't get the problem of fluorosis. So it's a very important measurement, and it's literally changed the lives of millions of people around the world.
You can cut your family's cavity rate almost in half. You too may hear,
Mom! Look, Mom, no cavities!
review, standards assure that measurements can be communicated and reproduced anywhere in the world. A kilogram is the same no matter where you are. In order to make chemical measurements, a variety of techniques have been developed. Sometimes the amount of a substance can be measured directly on a balance. More often, one substance is dissolved in another. It has to be measured indirectly using techniques like titration. Our health and our livelihoods depend on the chemistry of our environment, and measurement is the foundation of our ability to understand that chemistry.
I'm in an analytical laboratory. Someone has brought here a sample of some copper ore to be analyzed. Now, that analysis has to be believed by everyone when it leaves this laboratory. The chemists here have devised an elaborate procedure for doing it. The analysis begins with a careful weighing of the sample of the ore. Then in this hood it's digested with a very precise volume of perchloric acid. You know, when I think about it, what this is very much like a cookbook recipe. And just in the same way that no one would buy a copy of a cookbook in which the recipes were not repeatable, no one is going to believe the analytical chemist unless the prescription that he gives for the analysis is repeatable, not just here, but just as easily in Dar es Salaam or in Novosibirsk. What we have discussed in this program is how chemists determine what they have. The next logical question is to ask, how did it happen? Why? These we will look at in the next program.
Funding for this program was provided by the Annenberg CPB project.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And for information on this college telecourse, video cassettes, off-air videotaping, and books based on this series, telephone the Annenberg CPB project at 1-800-LEARNER.